Hello, my name is Abraham Chum, and this is a presentation on open channel flows and specifically the hydraulic jump. And this is my final project for advanced fluids. So just some motivation as to why we're studying open channel flows and the hydraulic jump. I've included this video. So it shows someone running water from a faucet over a flat red plate. And what we see is that when the person turns the water on, is that there is a sort of ring of water formed. And when he puts his finger down, we see something interesting happening as well. And this is a very everyday example, something that we see all the time, just when there are dishes in the sink. But it's interesting to see why this is actually happening. So that's sort of what I wanted to look at today. So just as an introduction to open channel flows, what we're sort of dealing with is this is a branch of hydraulics and fluid mechanics, and the open channel phrase refers to any sort of free surface. And so on the right side, we have a picture of some different types of flow, and the first two show flow in a conduit where it's completely closed, there's no exposure to any air or the environment, while the other three have are surrounded, by some sort of conduit, and on top we see exposure to the free surface. And so obviously, just in any sort of environment that introduces the impact of gravity. And the easiest example of this is looking at any river flowing through a bank. And specifically, if we look at the picture on the bottom, we see that the water in the river actually flows over something that is sometimes referred to as a weir. And so that we see the water flowing over that. And so that's actually what we're going to be looking at today. And so this is basically a study in compressible flow. Most fluid mechanics courses will actually study incompressible flow, which implements the assumption of constant density of whatever fluid you're studying. And so that basically boils down to us assuming that the fluid, any given volume of fluid will not, cannot change in size or in shape or any sort of thing like that. And so it is mostly studied with gases. But what this example actually shows, the example with the plate, helps us to analyze a quasi two-dimensional compressible flow of water situation where we're looking at water only in the plane of the flat plate. And so we'll be looking at compressible flows there where density actually can change. And so the easiest way that I thought to sort of introduce this topic was actually through a lot of things that I learned this semester taking a course in gas dynamics with Professor Sidebotham. And so we were looking at compressible flows of gases, mostly in the context of rocketry and different considerations for jet designs and things like that. And so what I wanted to introduce was the phenomena of normal and oblique shock waves. And that's easiest studied through by looking at the compression wave formation from an impulsive piston motion. And so we're looking at a piston that is just horizontal, and so the piston can move left and right. And what happens with a sort of instantaneous change in the piston, in the position of the piston, we see that there is a sort of wave that is formed of a higher density of fluid than the fluid that was originally there. And so when this when the flow with the higher density actually catches up to the original flow, there is a sudden decrease in the flow. And so what the major changes that we observe are that the Mach number decreases. The Mach number is something that is commonly used to just compare the velocity of the flow of gas to the speed of sound in that medium. And so that it's a ratio between that. And so we'll refer to those speeds as sonic. So if it's sonic, it is traveling at the speed of sound. The Mach number is 1. And so other changes are that density increases and that pressure increases. So this picture on the left is actually showing a normal shock, where the flow is traveling just completely normal, and the same thing is happening with the flow that has changed in density. But actually, in real life applications, specifically, for something like rocketry, we actually do see oblique shocks more often, and that happens with the compressive turning of supersonic flows. Again, supersonic means that the fluid is traveling at a speed faster than the speed of sound. And so just to look more into what happens with a shock is I've included the picture of a converging diverging nozzle. And so this is something that is commonly looked at in rocket science. So we see flow entering from a vacuum chamber from state 0 to 1. State 1 shows the throat of the nozzle. And what happens here is that the flow is actually choked there, which means the Mach number reaches 1. And the flow reaches the speed of sound. But the flow leaving the throat actually is supersonic, which means it accelerates. A compressive shock occurs at state 2, which means instantaneously the flow is taken from supersonic to subsonic. And we refer to something like this, and when we're looking at this, we look at something called the design point, where the pressure at state 4, the pressure immediately leaving the nozzle, matches the ambient pressure. Because if that's not the case, we have a pressure mismatch, which just includes an additional thrust for the rocket that we're looking at. And so it's not exactly the worst thing, and there are cases where the pressure mismatch is actually taken advantage of, but the design, the ideal design situation is where the pressures will match. And this is a good time to explain that the shock actually occurs because we want this pressure to match, and that's something that has just been observed. And as I mentioned before, what we see more often is that there are something called oblique shocks, where it will happen at an angle, not normal to the flow. And so we see that there is some sort of turn with a turning angle referred to as delta. And actually, depending on the angle of delta and the Mach number of the flow entering, we can observe two different types of oblique shocks. We can observe a weak shock and a strong shock, and depending on the Mach number, the weak shock will slow the flow but actually keep it supersonic, while the strong shock will turn it to completely subsonic flow, slower than the speed of sound. And on the right, we actually have some specific cases. So for a given Mach number, if the turning angle delta is greater than a certain number, we'll actually observe something called a detached shock. And so that is what is shown with this bow shock. We see that the shock sort of forms an interface that is separate from the actual object or wedge that that the flow is coming into contact with, and so we refer to that as coming into contact with a sort of blunt object, and so flow beyond that shock wave is subsonic. So just bring this back, sort of summarizing what we studied from rocket science and bringing this into fluids and looking into how this can be applied for the hydraulic jump. For gases, we looked at the Mach number, which again was comparing the speed of the flow to the speed of sound in that medium, while the Froude number is something that compares the speed of the fluid or the liquid, and compared to the speed of any wave in that medium. And so with rocket science, with gases, we refer to the speeds as supersonic or subsonic, while for liquids, we refer to them as supercritical or subcritical. And so we see those similar prefixes, which actually helps us to relate the two. And looking at the formula for the Froude number, we actually see that there is an extra dependence on the depth of the fluid. And so there are different considerations there with the height and how that actually plays an impact. So just going back to the video, now that we've sort of seen some sort of introduction and ways that we can approach this problem, I included a demo that I did at home, just in my kitchen sink, using the bottom side of a plate. So I actually start off by turning on the water very slowly. And so with the low flow of water, we see that the radius of the ring that is formed of the ring actually represents, inside the ring actually represents supercritical flow, while outside is the subcritical flow. And so as the flow of water gets higher and higher, we see that the ring is maintained for a larger radius. But then nevertheless, we still see that the ring is formed, and there's turbulence there, and we see that that's where the height increases. And again, I put my finger down, and this is where we can actually see that there is some sort of interface that is formed beyond my finger. And so that's sort of what we saw with the oblique shock occurring after the oblique shock occurring, where there is sort of something like a detached shock. And so beyond that sort of interface, we see subcritical flow. And so just looking at the actual thing that we wanted to study, the hydraulic jump, we have a rapid laminar flow region and a slower turbulent flow region. And we see in between those two regions a sudden increase in the height. And we sort of that's sort of a curious thing, because why would that sort of thing happen? And going back to why shocks occur, that was in order to match pressures. This actually happens because of the tendency of a fluid to match the height. So the hydraulic jump actually occurs because fluid that is flowing from somewhere else to a new surface, if the surface cannot maintain that supercritical flow, that's the hydraulic jump is what happens to account for that. And so it'll reach a point where the flow is subcritical, and that is what can be maintained by the surface. And so looking into the ways that we might want to study this flow, we typically look at the continuity equation as well as the momentum equation. And by looking, momentum actually is conserved in the hydraulic jump. And so by looking at that conservation, we can land upon something called the Belanger equation, which will help us to look at the ratio of the height right after the jump and right before the jump. And that actually is dependent on Froude number. And so for different Froude numbers, we'll see a different ratio of heights before and after the hydraulic jump. While momentum is conserved, energy actually is not. And so the energy dissipated through this jump can actually be determined as well using the different heights. So just some fluids concepts that this actually ties into is there can be some studies on boundary layer behavior, where we can consider the effects of drag and shear stress and on the boundary layer thicknesses, and what sort of considerations there are there. And there are, of course, varying degrees of turbulence that depend on the Froude number. And so sort of going from that into the next steps of study, on the right side, I've included a picture where for different Froude numbers, we see different flow profiles. We see different heights. We see different eddies forming. We see different considerations like that. And so for any different Froude number, I figured we could study something like the profile of the jump, the height ratios before and after the jump, how much energy is lost, and what degree of turbulence there is observed there. In addition to that, I also figured that we could study something like what happens to the hydraulic jump when there is some sort of barrier present. The reason I used the backside of the plate for my demonstration earlier was that when the plate that I was using was actually curved, and so when I used the upside, there was some sort of barrier, and the ring of supercritical flow was actually maintained for a lower amount of time. And seeing what sorts of things can happen when there is a barrier present. And that about wraps up my presentation, and just want to thank you for listening.